All right, we've looked at one-to-one. Now we're going to look at onto. It's kind of its cousin. A function f from x to y is onto if it hits every element of y. All right, so that means that f is onto if and only if for any y in y there exists an x in x so that f of x equals y. All right, so let's try again. Um, determine whether the following functions are onto. I have x squared again. Let me graph it. It's going to tell us where to go. I want to know if I hit every value of y. Of course, I do not. Y equals -1 would not work. So this function is not onto, as f of x is never -1. In fact, we know this. The square is always positive, and so every single negative value will not be hit. Definitely not an onto map. All right, let's try a second one. I want the map from -pi onto the pi onto. That sends an element to 10. If you remember, -pi onto is this vertical asymptote. Pi onto is the next one. And so the graph looks like this. It's going to hit every y value once. All right, so this is onto. In fact, if I take y in r, well, in -pi onto pi onto, I can take x, sorry, I had it right the first time. For every y in r, I can take x to be arctan of y, which is in -pi onto to pi onto, and tan of x is tan of arctan. These are inverse functions. They cancel, is y. And so, yes, my function's onto. All right, so let's keep going. I want to know when a linear transformation is onto. We had a really nice way of telling when it was one-to-one. We'll have a similar way of telling when it's onto. The following proposition is a direct consequence of the definition of image. Turns out it's much easier to prove this than it was for the kernel. We won't need a separate proof. The image tells us exactly what's going on. If I have two vector spaces, a linear transformation is onto if and only if the image, well, if it hits everything, so the image is W. All right, assume that W is finite dimensional. A linear transformation is onto if and only if what hits everything, so the rank of T is the dimension of W. All right, let's look back at our trace example from last video. Example 2.2.6, we'll look at the trace. A gets mapped to the trace of A. I want to show that the trace is onto. All right, so we want to talk about its rank and show that it is, well, the same dimension as R. So we need that the rank of T is the dimension of R, which is 1. Well, it can't be more than 1 because the the image is inside R, and so the only thing that it could be is 0. So we just need to find a non-zero element in the image of the trace, just to make sure that it's not just a 0 map. So let's see. I'm going to look at the trace applied to 1 and then a bunch of zeros. that's, well, actually, let me put 2 just because I don't want to look like I'm doing this one, is equal to 2. So 2's is in the image of trace. So the image of trace isn't just 0, but the only other possibility, right? These are, let me write it here just to make sure it's clear. Image of trace is a subspace of R, which has dimension 1, so only 2 options. Either the image of trace is 0 or the image of trace is all of R. And so all we have to do is to show that there is one that doesn't belong here, and then you'll be here. All right, let's stop here.